Testing. I should be live, but CL is being quiet. Hello. Okay. Hi. Good time of day. Okay, there we are. Okay, let's start. Yes, I'm here. Finally. So yeah, good time of day, whether it's morning, afternoon, night, or any other time. I don't know what other times there are. Today, we are here because we should do more learning. Ta-da! I was really excited about the NLP lesson, so I wanted to come back as soon as possible, and as soon as possible is like this many days later, so yes. So what are we doing? Why are we here, and what's the reason? Yes, it does. It is more NLP, that's for sure. That's what it looks like. I think today will be all NLP, so I'm really excited about that. Also, hello. On the YouTube and Twitch side. I think I asked once, but do you prefer being called by your full name, or is there a shorter name that you prefer being called by? Please let me know, because I am curious. Small FYI, like during the past 48 hours, I don't know why, but my YouTube channel has like gotten like over 10 subscribers or something, and I'm like, what did I do? Because like I don't mind getting subscribers, but I've been losing them for quite a bit, because people came for hashcode, and I'm no longer doing hashcode because that's no longer there. So I was pleasantly surprised, not subscribed. There we go. I was pleasantly surprised there. Forgot to say it again. Yes. So, today we are here to take lesson 11, if you can believe that, of the Introduction to Machine Learning for Coders course taught by Jeremy, the amazing Jeremy Howard. I really answered to mostly in coffee is okay though, it's shorter. Maybe just interest in AI growing. Sure. Yes. I just think that I have problem, like there's also like the audio part, but the visual part, like the computer vision, it feels out of my depth because I wasn't with it more. Like, yeah, I feel like NLP maybe is growing more, and it's, I don't know, maybe I've been with it more. Not sure. Yes. So, lesson 11. Fast AI. Today, after a review of the math behind the naive Bayes, we'll do a deep dive into embeddings, both as used for categorical variables in tabular data and as used for words in NLP. Okay, tabular data and NLP. I think failed to save draft, that's mean. how far did we go with this? Am I not logged in? Do I need to refresh? I think we went as far as... Oh yeah, no, we didn't get to trigrams. I know we were talking about n-grams, but we didn't go that far. I think we were just like here. Let's see. Oh, muted. There. You know, when you start something, you say Bismillah, as in, so that it starts well. So let's start this lesson.
So let's start by reviewing kind of what we've learned about optimizing multi-layer.
I think this ML stuff is probably good for vision as well. Like traditionally, vision ML was very much about handcrafting algorithms and stuff. Oh, look, Jeremy Harris is saying something. Yeah. I think like the past decade, maybe less, like, I don't know, 8-9 years of computer vision is all based on neural nets, right? So yeah, it's ML had Vision had its spring, I don't know what it's called, like, and now NLP is having it. Do you know what I'm saying? What is it called? Things that, I don't know. Like it's in season, you know? It's fashionable. Vision used to be like that, and now NLP is like that. So yeah, they did benefit from it. Like they feed pixels through transformers. Aha! As like a bit line, basically almost like text. I don't know. I don't have information about. Oh yeah, Dolly and Stable Vision are also having their day. Yep. You're right. You're absolutely right. Generative AI for anything is having its day. That I agree with you.
Functions with SGD. And so the idea is that we've got some data, and then we do something to that data. For example, we multiply it by a weight matrix. And then we do something to that. For example, we put it through a softmax or a sigmoid. And then we do something to that, such as do a cross-entropy loss or a root mean squared error loss. Okay, and that's going to like give us some scalar. Oh.
And that's based on denoising. Like train it with an image, you add noise to it and train it to remove the noise until you can give it the just noise and have it made a picture. I actually saw that in a video. It's really surprising, like a surprising method. Can you do that to language? Yeah, just give it noise and it will give you a picture. I've seen that. I mean, I've seen that demonstrated, and it's a really cool and weird method. And I like this box in a box in a box.
So this is going to have no hidden layers. This has got a linear layer, a nonlinear activation being a softmax, and a loss function being a root mean squared error or a cross entropy. All right. And then we've got our input data.
That makes sense.
Input, linear, nonlinear.
You can. Huh. I should look for that.
Loss. So for example, if this was sigmoid,
But because it takes more steps to denoise, it hasn't been popular with language. I bet. Like, do you give it noise by giving it words or letters or punctuation? Because like noise in image is obvious. At least I think it's obvious. But like, give it to a child and say which one is noise and which one is a QR code. Would they recognize it? I don't know. Yeah. This is really fun.
or softmax, and this was cross entropy, then that would be logistic regression. So it's still yeah. Cross entropy? Yeah, let's do that next. Sure. For now, think of root mean squared error. Same thing, some loss function. Okay, for now. We'll look at cross entropy again in a moment. So how do we calculate the derivative of that with respect to our weights, right? So really, it would probably be better if we said x comma w here, because it's really a function of the weights as well. And so we want the derivative of this with respect to our weights.
Okay.
Oh, sorry, I put it in the wrong spot. G f of x comma w. I just screwed up, that's all. That's why that didn't make sense. All right. So to do that, we just basically do the chain rule. So we just say that this is equal to h of u, and u equals u equals g of v, and v equals f of x.
Okay.
So we can just rewrite it like that, right? And then we can do the chain rule. So we can say that's equal to h dash, the derivative is h dash u by g dash v by f dash x. Happy with all that so far? Okay. So in order to take the derivative with respect to the weights, therefore we just have to calculate that derivative with respect to w using that exact formula. So if we had in there, so d of all that, dw, would be that. Yeah. So then if we went further here and had like another linear layer, right? Let's give us a bit more room. Another linear layer.
Outside of all this?
Comma, I don't know, W2.
Oh, why?
Right?
Is
so
it?
we have another linear layer.
Okay.
There's no difference to now calculate the derivative with respect to all of the parameters. We can still use the exact same chain rule, right? So don't think of the multi-layer network as being like things that occur at different times. It's just a composition of functions. And so we just use the chain rule to calculate all the derivatives at once. They're just a set of parameters that happen to appear in different parts of the function, but the calculus is no different. So to calculate this with respect to W1 and W2, it's just, you just increase, W, you can just now just call it W and say W1 is all of those weights. So the result, that's a great question. So what you're going to have then is a list of parameters, right? So here's W1, and like it's probably some kind of higher rank tensor, you know, like if it's a convolutional layer,
Okay.
it'll be like a rank 3 tensor or whatever, but we can flatten it out, right? We'll just make it a list of parameters. There's W1, here's W2, right? It's just another list of parameters.
So these are, yeah,
right?
our weights.
And here's our loss, which is a single, you know, a single number. So therefore, our derivative is just a vector of that same length, right? It's how much does changing that value of W affect the loss? How much does changing that value of W affect the loss, right? So you can basically think of it as a function like, you know, y equals ax1 plus bx2 plus c,
That's
right?
his mouse,
And
not
say
mine.
like,
Okay.
oh, what's the derivative of that with respect to a, b, and c?
Moving my
and
mouse
you would have
around.
3 numbers, the derivative with respect to a, and b, and c. And that's all this is, right? It's a derivative with respect to that weight, and 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 that weight. To get there, inside the chain rule, we had to calculate, and I'm not going to go into detail here, but we had to calculate like Jacobians. So like the derivative when you take a matrix product is you've now got something where you've got like a weight matrix, and you've got an input vector. These are the activations from the previous layer, right? And you've got some new output activations, right? And so now you've got to say like, okay, for this particular weight, how does changing this particular weight change this particular output? And how does changing this particular weight change this particular output? And so forth. So you kind of end up with these higher dimensional tensors showing like for every weight, how does it affect every output, right?
Okay.
But then by the time you get to the loss function is going to have like a mean or a sum or something. So they're all going to get
One
added
value.
up in the end. You know? And so this kind of thing, like, I don't know, it drives me a bit crazy to try and calculate it out by hand or even think of it step by step, because you tend to have like, you just have to remember for every input in a layer, for every output in the next layer, you know, you're going to have to count for every weight, for every output.
Oh no. No, 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 no. Wait. Wow, okay. Yes, I should be live. Okay. Yeah, no worries. You know the name of the app, that's cool. Yeah, just double checking if I'm live or not. And I think I am, which is good. Okay. I just saw you're offline, and that scared me, so I was so into the lesson. I'll get the model back in a bit. Yeah.
One good way to look at this is to learn to use PyTorch's like .grad attribute and .backward method manually, and like look up the PyTorch tutorials, and so you can actually start setting up some calculations with a vector input and a vector output, and then type .backward, and then say type .grad, and like look at it, right? And then do really small ones with just 2 or 3 items in the input and output vectors and like make the operation like +2 or something, and like see what the shapes are, make sure it makes sense. Yeah, because it's kind of like this vector matrix calculus is not like introduces zero new concepts to anything you learned in high school, like strictly speaking, but getting a feel for how these shapes move around, I find took a lot of practice. You know, the good news is you almost never have to worry about it.
I worry about everything.
Okay, so we were talking about then using this kind of logistic regression for NLP. And before we got to that point, we were talking about using naive Bayes for NLP. And the basic idea was that we could take a document, right, a review, like this movie is good, and turn it into a bag of words representation consisting of the number of times each word appears, right? And we call this the vocabulary. This is the unique list of words.
Yes.
Okay. And we used the sklearn count vectorizer to automatically generate both the vocabulary, which in sklearn they call the features, and to create the bag of words representations, and the whole group of them then is called a term document matrix. Okay, and we kind of realized that we could calculate the probability that a positive review contains the word this by just averaging the number of times this appears in the positive reviews, and we could do the same for the
negative one,
and we could do the same for the negatives, right? And then we could take the ratio of them to get something which, if it's greater than 1, was a word that appeared more often in the positive reviews, or less than 1 was a word that appeared more often in the negative reviews. Okay, and then we realized, you know, using Bayes' rule that and taking the logs, that we could basically end up with something where we could add up the logs of these plus the log of the ratio of the probabilities that things are in class 1 versus class 0, and end up with something we can compare to 0. If it's a bit greater than 0, then we can predict a document is positive, or if it's less than 0, we can predict the document is negative. And that was our Bayes rule, right? So we kind of did that from math first principles, and I think we agreed that the naive in naive Bayes was a good description, because it assumes independence when it's definitely not true.
Yes,
but it's an interesting starting point, and I think it was interesting to observe when
we said that the words are not independent, so then we went to n-grams because of that.
Actually got to the point where, like, okay, now we've, you know, calculated the ratio of the probabilities, and took the log, and now rather than multiplying them together, of course, we have to add them up. And when we actually wrote that down, we realized, like, oh, that is, you know, just a standard weight matrix product plus a bias, right? And so then we kind of realized, like, oh, okay, so like if this is not very good accuracy, 80% accuracy, why not improve it by saying, hey, we know other ways to calculate a bunch of coefficients and a bunch of biases, which is to learn them in a logistic regression, right? So in other words, this...
Americans probably still use naive Bayes because of grams. Ha! That's actually funny. That's a good joke. You should definitely tweet that. Yeah. We're past that. We use metric, but Americans are still using n-grams. Because they have to be different, don't they?
This is the formula we use for a logistic regression. And so why don't we just create a logistic regression?
Yes.
Okay, and it's going to give us the same thing, but rather than coefficients and biases which are theoretically correct based on, this assumption of independence and based on Bayes' rule, there'll be the coefficients and biases that are actually the best in this data. Okay? So that was kind of where we got to. And so the kind of key insight here is, like, just about everything I find in machine learning ends up being either like a tree or a bunch of matrix products and nonlinearities, right? Like everything seems to end up kind of coming down to the same thing, including, as it turns out, Bayes' rule. Right? And then it turns out that nearly all of the time, then whatever the parameters are in that function, nearly all the time it turns out that they're better learnt than calculated based on theory. Right? And indeed that's what happened when we actually tried learning those coefficients. We got 85%. Okay. So then we noticed that we could also,
these?
rather than take the whole term document matrix, we could instead just take the ones and zeros for presence or absence of a word.
I do remember that because I think the percentage was 89.
And sometimes it was
still 85.
Equally as good. But then we actually tried something else, which is we tried adding regularization, and with regularization, the binarized approach turned out to be a little better.
Okay.
Right? So then regularization was where we took the loss function.
Isn't it this one? It was just a parameter, wasn't it?
Right, and again, let's start with RMSE, and then we'll talk about cross entropy.
Okay.
Loss function was our predictions minus our actuals, sum that up, take the average, plus
alpha,
a penalty.
Oh.
Okay, and so this specifically is the L2 penalty. If this instead was the absolute value of W, then that would be the L1 penalty. Okay. We also noted that we don't really care about the loss function per se. We only care about its derivative. That's actually the thing that updates the weights. So we can, because this is a sum, we can take the derivative of each part separately. And so the derivative of this part was just that, right? And so we kind of learnt that even though these are mathematically equivalent, they have different names. This version is called weight decay, and it's kind of what's used, that term is used in the neural net literature. Okay. So cross entropy, on the other hand, it's just another loss function like root mean squared error. But it's specifically designed for classification, right? And so here's an example of binary cross entropy. So let's say this is our, is it a cat or a dog? So let's just say, is cat 1 or a 0? So cat, cat, dog, dog, cat. And these are our predictions. This is the output of our final layer of our neural net or our logistic regression or whatever. All right. Then all we do is we say, okay, let's take the actual times the log of the prediction, and then we add to that 1 minus actual times the log of 1 minus the prediction.
Why?
And then take the negative of that whole thing. All right? So I suggested to you all that you tried to kind of write the if statement version of this, so hopefully you've done that by now, otherwise I'm about to spoil it for you. So this was y times log y plus 1 minus y times log 1 minus y, right? And negative of that. Okay, so who wants to tell me how to write this as an if statement?
Why would that be an if statement?
All right, Chen-Shi, hit me.
I'll give it a try. So
Yes, sir.
if y equal to if y equal to 1,
Mm-hmm.
then return log y.
Mm-hmm.
Okay.
Otherwise, else return log 1 minus 1.
Good.
Because that's the thing in the brackets, and you take c minus.
Good. So the key insight Chen she's using is that y has two possibilities, 1 or 0. Okay? And so very often the math
I see.
can hide the key insight, which I think happens here until you actually think about what the values it can take are, right? So that's all it's doing. It's saying either give me that or give me that, right? Could you pass that back, please, Jinshi?
Sorry if I'm missing something, but do you not need two variables in that statement? Because you got y. Shouldn't it be like a y hat and a y or something?
Oh, yeah. Thank you. As usual, it's me missing something. Okay. Okay, and so then the multi-category version is just the same thing, but you're saying, it for different, more than just y equals 1 or 0, but y equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, for instance. Okay. And so that, that loss function has you can figure it out yourself, and particularly simple derivative. And it also, another thing you could play with at home, if you like, is like thinking about how the derivative looks when you add a sigmoid or a softmax before it. It turns out it all turns out very nicely because you've got an xb thing going into a loggy thing, so you end up with, very well-behaved
XB thing going into a loggy thing.
The reason, I guess, there's lots of reasons that people use RMSE for regression and cross-entropy for classification, but most of it comes back to this statistical idea of a best linear unbiased estimator, and based on the likelihood function, it kind of turns out that these have some nice statistical properties. It turns out, however, in practice, root mean squared error in particular, the properties are perhaps more theoretical than actual, and actually nowadays using the absolute deviation rather than the sum of squareds deviation can often work better. So in practice, like everything in machine learning, I normally try both. For a particular data set, I'll try both loss functions and see which one works better. Unless, of course, it's a Kaggle competition, in which case you're told how Kaggle's going to judge it, and you should use the same loss function as Kaggle's evaluation metric.
Right.
All right. So yeah, so this is really the key insight, is like, hey, let's not use theory, but instead learn things from the data, and we hope that we're going to get better results, particularly with regularization, we do. And then I think the key regularization insight here is, hey, let's not try to reduce the number of parameters in our model, but instead use lots of parameters and then use regularization to figure out which ones are actually useful. Right? And so then we took that a step further by saying, hey, given we can do that with regularization, let's create lots more features by adding bigrams and trigrams. Bigrams like by vast and by vengeance, and trigrams like by vengeance full stop and by Vera Miles.
By fast, right? And by furious.
And, just to keep things a little faster, we limited it to 800,000 features, but, even with the full 70 million features, it works just as well, and it's not a hell of a lot slower. So we created a term document matrix, again, using the full set of n-grams for the training set, the validation set. And so now we can go ahead and say, okay, our labels is the training set labels as before. Our independent variables is the binarized term document matrix as before. And then let's fit a logistic regression to that.
Regularized. And, 0 and 1 of the bag of words, right?
Let's do some predictions, and we get 90% accuracy.
I don't think I ran that, so let's run. Do I need to rerun everything? Seems that way, doesn't it? Because I don't have anything saved. Well, no, it's already there. Well, that's gonna take a while.
So this is looking pretty good. Okay. So the logistic regression, let's go back to our naive Bayes, right? In our naive Bayes, we have this term document matrix, and then for every feature, we're calculating the probability of that feature occurring if it's class 1, that probability of that feature occurring if it's class 2, and then the ratio of those two, right? And in the paper that we're actually basing this off, they call this P, this Q, and this R, right? Maybe I should just fill that in. P, Q.
Why though?
Maybe then we'll say probability to make it more obvious. Okay. And so then we kind of said, hey, let's not use these ratios as the coefficients in that matrix multiply, but let's instead like try and learn some coefficients, you know, so maybe start out with some random numbers, you know, and then try and use stochastic gradient descent to find slightly better ones. So you'll notice, you know, some important features here. The R vector is a vector of rank 1, and its length is equal to the number of features. And of course, our logistic regression coefficient matrix is also of rank 1, and length equal to the number of features, right? And we're saying like they're kind of two ways of calculating the same kind of thing. Right? One based on theory, one based on data. So here is like some of the numbers in R, right? Remember it's using the log, so these numbers which are less than 0 represent things which are more likely to be negative, and these ones here are more likely, this one here is more likely to be positive. And so here's e to the power of that, and so these are the ones we can compare to 1 rather than to 0. So I'm going to do something that hopefully is going to seem weird.
Okay. Before you do that. Okay.
And so first of all, I'm going to say what we're going to do, and then I'm going to try and describe why it's weird, and then we'll talk about why it may not be as weird as we first thought. So here's what we're going to do. We're going to take our term document matrix, and we're going to multiply it by R.
Okay.
So what that means is we can do it here in Excel, right? So we're going to say, let's grab everything in our term document matrix and multiply it by the equivalent value in the vector of R. Right? So this is like a broadcasted element-wise multiplication, not a matrix multiplication. Okay? And that's what that does. Okay, so here is the value of the term document matrix times R. In other words, everywhere that a 0 appears there, a 0 appears here, and every time a 1 appears here, the equivalent value of R appears here. So we haven't really changed much, right? We've just kind of changed the ones into something else, into the R's from that feature, right? And so what we're now going to do is we're going to use this as our independent variables instead in our logistic regression. Okay, so here we are, multiply x NB, x naive Bayes version is x times R, and now let's do a logistic regression fitting using those independent variables. And let's then do that for the validation set, okay, and get the predictions, and lo and behold, we have a better number. Okay, so let me explain why this hopefully seems surprising. Given that we're just multiplying... Oh, I picked out the wrong ones. I should have said R, not coef.
Yeah, I noticed.
Okay, that's actually R. I got the wrong number. Okay, so that's our independent variables, right? And then the logistic regression has come up with some set of coefficients. Let's pretend for a moment that these are the coefficients that it happened to come up with, right? We could now say, well, let's not use this set. Let's not use this set of independent variables, but let's use the original binarized feature matrix, right? And then divide all of our coefficients by the values in R.
Okay.
And we're going to get exactly the same result mathematically. So, you know, we've got our X naive Bayes version of the independent variables, and we've got some set of weights, some set of coefficients. I call it W, right? W1, let's say, where it's found like this is a good set of coefficients for making our predictions from, right? But X and B is simply equal to X times, as in element-wise, times R, right? So in other words, this is equal to X
R
times R times the weights. And so, like, we could just change the weights to be that, right? And get the same number. So this ought to mean that the change that we made to the dependent variable shouldn't have made any difference.
But
because
it
we
did.
can calculate exactly the same thing without making that change. So there's the question. Why did it make a difference? So in order to answer this question, I'm going to try and get you all to try and think about this. In order to answer this...
This good is really high, and that should help. And the bad is really low. So, is it about context? I don't know.
You need to think
I
about,
don't think
like,
so.
okay, what are the things that aren't mathematically the same? Why is it not identical? What are the reasons? Like, come up with some hypotheses. What are some reasons that maybe we've actually ended up with a better answer? And to figure that out, we need to first of all start with, like, well, why is it even a different answer? Why is that different to that?
Oh,
This is subtle. All right, what do you think?
I was just wondering if there was two different kinds of multiplications. You said that one is the element-wise multiplication.
No, they do end up mathematically being the same.
Okay.
Pretty much. There's a minor wrinkle, but it's not that. It's not some order operations thing. Worth a try. Kenchi? You are on a roll today, so let's see how you go.
I feel like the features are less correlated to each other.
I mean,
Like
I've made a claim that these are mathematically equivalent. So what are you saying, really? You know, why are we getting different answers?
because they're looking at different numbers, aren't they?
Keep on coming up with hypotheses. We need lots of wrong answers.
Are we being mean to the movie? If it's good or bad? Like maybe irrelevant stuff is more a factor? Really? But I mean, what I'm saying is that we're giving more what's the word? Weight, importance to the words that matter. And you're saying that irrelevant stuff is more of a factor, so I don't know. Let's see.
Before we start finding it's the right ones. It's like that, warmer, hotter, colder, Ernest, are you going to get us hotter?
Does it have anything to do with the regularization?
Yes.
And is it the fact that when you...
So let's start there, right? So Ernest's point here is like, okay, Jeremy, you've said they're equivalent, but they're equivalent outcomes, right? But you went through a process to get there, and that process included regularization, and they're not necessarily equivalent regularization. Like our loss function has a penalty.
Yes.
So yeah, help us think through, Ernest, how much that might impact things.
Well, this is me being kind of dumb, but I'm just noticing that the numbers are bigger in the ones that have been weighted by the naive phase, R weights. And so
these are bigger, and some are smaller, some are bigger.
right, but
there are some bigger ones.
Like the variance between the columns is much higher now.
The variance is bigger. Yeah, I think that's a very interesting insight.
Okay, that's all I got.
Okay, so build on that.
I don't like building. Thank you.
Prince has been on a roll all month, so hit us.
Actually, I'm not sure,
That's
but
fine.
is it also considering the dependency of different words? Is that why it is performing better, rather than all words independent of each other?
Not really. I mean, it's again, theoretically, these are creating mathematically equivalent outputs. So they're not doing something different, except, as Ernest mentioned, they're getting impacted differently by regularization. So what's regularization, right? Regularization is we start out with our that was the weirdest thing. I forgot to go into screenwriting mode, and it just turns out that you can actually write in Excel, and I had no idea that was true. I still use screenwriting mode so I don't kill up my spreadsheet. I never tried. So our loss was equal to like our cross entropy loss, based on the predictions, or the predictions and the actuals, right? Plus our penalty. So if your weights are large, right, then that piece gets bigger,
Yes.
right, and it drowns out that piece, right? But that's actually the piece we care about, right? We actually want it to be a good fit. So we want to have as little regularization going on as we can get away with. We want to have less weights.
So we make
here's
the other
thing,
side bigger?
right? Our value, yes, can you pass it over here?
When you say less weights, did you mean lesser weights?
I do, yeah. And I kind of use the two words a little equivalently, which is not quite fair, I agree. But the idea is that weights that are pretty close to zero are kind of not there. Yeah. So here's the thing. Our values of R, and I'm not a Bayesian weenie, but I'm still going to use the word prior, right? They're kind of like a prior. So like we think that the different levels of importance and positive or negative of these different features might be something like that, right? We think that like bad, might be more correlated with negative than good, right? So our kind of implicit assumption before was that we have no priors. So in other words, when we said squared weights, we're saying a non-zero weight is something we don't want to have.
Right.
But actually, I think what I really want to say is that differing from the naive Bayes expectation is something I don't want to do, right? Like only vary from the naive Bayes prior unless you have good reason to believe otherwise. Right? And so that's actually what this ends up doing, right? We end up saying, you know what? We think this value is probably 3, right? And so if you're going to make it a lot bigger or a lot smaller, right, that's going to create the kind of variation term to go up, right? So if you can, just leave all these values about similar to where they are now.
Cool.
Right? And so that's what the penalty term is now doing, right? The penalty term, when our inputs is already multiplied by r, is saying penalize things where we're varying it from our naive Bayes prior. Can you pass that there?
I need to go. And this was fun. And I feel like I understood some things. But not too much, just enough. Yeah. I think you heard my timer, which is, not, I shouldn't do that. But yes. So it is time for us to say goodbye. Oh, well, yes. Thank you for coming by. I hope you enjoyed the lesson. Thank you for the stream. Are you likely to stream tomorrow? The answer is yes, but wish me luck. Yeah, yes, it was easy for me to stream today, so hopefully if the situations, the variables don't change, then hopefully the answer should be yes. What was I saying? I was saying we didn't get to embeddings. It was mostly review, and I like that. So hopefully we'll get to embeddings, inshallah, tomorrow. Thank you for being here. Thank you for your time. I hope you learned something. And I'm gonna end the stream. Oh, by the way, I just want to say that the stream today was not horrible. There was a few cuts, but I hope it wasn't as horrible. Anyway, I'm gonna do the countdown from 5 and say thank you. I appreciate you. And you don't have to come back, but if you do, I appreciate that as well. So, ending the stream in 5,